For Pi Day this year, I wanted to make a video talking about the various algorithms for computing pi and showcase some programs which do this. As many of you may already know, the definition of pi comes from the circle. To be precise, first we pick a center point, then a circle is defined to be a set of points which are equidistant from this center. A diameter is defined as a line passing through the center which starts and stops on the circle, and a radius is simply half of that length. Finally, pi is defined to be the ratio between the circumference of the circle and the diameter, which you may already recognize as approximately 3.14 and so on. Now let's talk about why you should care about calculating the digits of pi. So pi has been calculated to an increasingly better accuracy for thousands of years, with famous people like Archimedes and Leonard Euler even contributing a few digits. As of making this video, the world record for pi sits at 200 trillion digits. So yeah, people are most definitely doing it just for fun nowadays. The reason why I'm so interested in pi? Simple, code golf. It's this wacky competition where programmers try to calculate digits of pi using the tiniest bits of code possible, instead of going outside, of course. I've not seen the sun myself in the last 3 days, as I've been trying to grind my way up the leaderboard. So let me tell you about the techniques I've used to achieve a score which is only 2 characters away from first place. But before I tell you my secrets, we must first appreciate how Grandpa Archimedes was able to determine pi to 2 decimal places back in 250 BC, while everyone else in the world were busy bashing each other in the head with rocks or something like that. So Archimedes came up with the trick of drawing polygons inside and around a circle, and then using them to produce bounds on the circumference. Observe that the inscribed polygon clearly has a perimeter less than the circumference, which in this case is the green square. And the circumscribed polygon has a perimeter larger than the circumference, which in this example is the red square. Next, we can compute the side lengths of the green square by using the Pythagorean theorem on the 2 yellow radii which I've drawn, in this case coming out to r root 2. Next, by looking at the white diameter I drew, the red square clearly has a side length of 2r. Now we can use the fact that the circumference must be wedged between the perimeters of the squares to produce a relatively awful bound on pi. Let's repeat the example, but with a hexagon. From drawing these 2 radii, we form an equilateral triangle with the inscribed hexagon, meaning its side length is just r. But for the circumscribed hexagon, I will draw a yellow radius and a purple line connecting from the center to one of its vertices. On the right, we have a 30, 60, 90 triangle, also known as a 1, 2, root 3 triangle, of which the latter naming is due to the ratio of its side lengths. You've guessed it, the 2 lines I've drawn on the left indeed form a 1, 2, root 3 triangle, and both of these triangles have their respective edges matching in color. Using the 1, 2, and root 3 ratios, we can identify the red and purple lengths based on the yellow side, which is just the radius r. Let's quickly rationalize the denominators. From there, we can repeat the same process and create bounds on pi, and this time they are slightly better. But you might be asking me, how did Archimedes get pi to 2 digits then? For that, I leave this 96-sided polygon as an exercise to the viewer. So Archimedes gave us a geometric approach, but what if we want a repeatable process that we can iterate on to produce more and more digits of pi? The Leibniz series does exactly that, and it computes pi over 4 by summing the alternating series of 1 divided by the odd numbers. I will show you a proof of this result. First and foremost, let's find the derivative of the arctangent function. Let's begin with y equals arctan of x. By definition, then x is equal to tan of y. Taking the derivative of both sides now, we get that dx by dy is equal to secant squared of y. Using the trig identity for tan squared and secant squared, we get that this is equal to 1 plus tan squared of y. But since x is equal to tan of y, this is actually equal to 1 plus x squared. Finally, we can flip the fraction to get dy by dx is equal to 1 over 1 plus x squared. Now, by the fundamental theorem of calculus, we can reverse the derivative by taking the integral. The integral from 0 to x of 1 over 1 plus t squared dt gets us back arctan of x. For our next lemma, we will expand the expression 1 over 1 plus t squared. The first equation simply plugs minus u to the power of 2n plus 1 into the finite geometric series formula. We can then simplify the left-hand side by cancelling out the negatives. Next, we can split the fraction on the left-hand side. Then, we will move the second term to the right-hand side. Now what we have is this nice alternating geometric series, subtracted by an ugly term at the end. And finally, we will substitute u equals t squared to achieve the desired expansion of 1 over 1 plus t squared. Now we are ready for the proof. Let's first assume that x is between 0 and 1. We will need this for later. Start with our expansion for 1 over 1 plus t squared, and then take the integral from 0 to x dt. I've left out the last term intentionally, and used the power rule to integrate all the other terms. Now to get rid of the last term, we will take the limit of the entire expression as n goes to infinity. This term disappears because when we integrate, we will get a 4n plus 3 term in the denominator, using the power rule. And since x is between 0 and 1 from our initial assumption, the 4n plus 3 term grows much faster as we take the limit, and hence the entire term vanishes. By the way, I have no idea what the integral actually comes out to be, so I wrote O of x to the 6n instead. You're welcome. Observe that the number of terms now becomes infinite from taking the limit. Hey, how come the left-hand side looks kind of familiar? That's because it's equal to arctan x from our first lemma. And given that n is not in the expression, we simply drop the limit on the left-hand side. Now we can plug in x equals 1 to get that pi over 4 is equal to 1 minus a third, plus a fifth, minus a seventh, and so on. But how does the Leibniz series perform in practice? Well, the unfortunate reality is that it's complete and utter garbage. I ran a few experiments in Python and plotted a graph comparing the number of accurate digits of pi computed on the y-axis versus the number of iterations on the x-axis, which is also equivalent to the number of terms summed up in the series. You may notice that the graph looks rather linear, which is not a good sign. Since the x-axis is the base 10 logarithm of the number of iterations, then reading from the graph, we need approximately 10 terms to compute 2 accurate digits of pi, 100 terms for 3 digits, 1,000 terms for 4 digits, and so on. My toaster of a PC can't really handle running more iterations without turning into a jet fan and burning down my apartment, so the graph is cut off at 10 to the 6, or about 1 million iterations. As a fun fact, you need about 5 billion terms of the Leibniz series to compute 10 decimal places of pi, if you run it long enough, I guess. Alright, all jokes aside, here's a simple Python implementation of this series. We are using the decimal library to get more precision for floating point arithmetic. Again, this approach will never even work, as we see that 10 to the 6 or 1 million iterations only gives us 5 decimal places. Using a convergence rate of O of 1 over n, we would need somewhere in the order of 10 to the 1,000 terms to pass the judge on code golf. Just for fun, I quickly golfed the previous implementation down to 77 characters. Feel free to pause and read the code. Well, if the Leibniz series doesn't even work in practice, then why did I spend all that time in the video talking about it? Well, as Master Uguay says,
you must believe.
Master!
So the convergence rate of alternating series can oftentimes be quite poor, with the Leibniz series oscillating up and down, maintaining a substantial error from pi. Every time we add or subtract a term, we go a little too far to the other side. Euler discovered that you can actually accelerate the convergence of an alternating series by converting it to a non-alternating form. This is achieved by shuffling the terms around, and it is known as the Euler transform. We can break each of A0, A1, A2, etc. into halves. Then we group the terms in pairs like this, with the odd one out being the first A0 over 2 term. Now let's apply this to the Leibniz series. We take half of 2 to create 2, and half of 4/3 to create 2/3. Then we regroup them as per the Euler transform. To continue the analysis, I've simplified the fractions and rewritten the denominators as products of odd numbers. This will be a recurring pattern. Lastly, we will write this as a summation and call it S1 to denote that we've applied the Euler transform exactly once. Now let's take S1 and apply the Euler transform again, but we don't touch the isolated 2 term we created from S1. This pulls out yet another term, 2 over 3. Now we can write out S2. Let's repeat this process again to produce S3, which has an extra 4 over 15 term. I've displayed S1 through S5 here so the pattern becomes easier to spot. Not obvious? Don't worry, me neither. But from hours of suffering, I will lay it out for you. From looking at the isolated terms of S5, we see that the denominators are simply the products of the odd numbers, and the numerator is equal to 2 times k factorial. Taking the limit as n goes to infinity, we can write the entire summation for pi consisting of only positive terms. There is an extremely interesting way that we can rewrite the sum. We can express this as an infinitely nested equation consisting of multiplications and additions. Observe that we can get the coefficient of 2 from the constant 2 terms, and we can get n factorial over the product of the odd numbers by multiplying out the nested fraction terms. Lastly, we can rewrite the denominator as the double factorial of 2k plus 1, which is just some fancy notation for the product of the first k plus 1 odd numbers. You've probably been waiting for this, as it took us a long journey to arrive at this expression for pi. I can tell you that I used these formulas to achieve my top scores for this problem on Code Golf. And to showcase just how short this code can get, let's begin with a naive implementation. Here we are using the summation form of this expression, by iteratively calculating the numerator 2 times k factorial, and denominator 2k plus 1 double factorial. Then in each iteration, we add one of these terms. Observe that we only need to iterate less than 3,500 times to accurately produce pi to 1,000 decimal places. Note that we again use the decimal library for 1,000 digits of floating point precision. We also need a bit more precision past the 1,000th decimal place to create an accuracy buffer for the last few digits. Without giving too much away, here's a somewhat golfed version in plain text. We were able to substantially cut down the size of this, and there are many more tricks you could do, both math and Python-wise, to shrink it down even further. Last but not least, I will show a censored UTF-16 encoded version of my 60-character top solution. The characters don't even display properly in the Manum code block, so here's an image from Code Golf instead. I'm very sorry that I can't show you the plain text. That would both ruin the fun of the challenge, and might just get me banned off the damn website. Just kidding, they'll never actually find where I live, because I use... never mind, I don't have a sponsor. Something you might be wondering is, how did I know to use a transformed version of the Leibniz series for pi? Well, the answer is, I literally didn't know anything. I spent a dozen hours trying everything I could find. I was looking on Wolfram Alpha, Wikipedia, and even reading random papers. Thank you so much for making it to the end of my first YouTube video. I hope you enjoyed and maybe even learned a single thing or two. If this project all seems a little rushed, it's because I started it less than a week ago and grinded my ass off to get it in by Pi Day. Here you can see my jam-packed schedule, and honestly I should have taken more breaks. Please subscribe if you feel bad for me. Anyways, I'll put up a poll so you can vote on a future video idea, and if this video gets 100 likes, I will make another video based on the most popular choice. Well, that pretty much concludes everything. See you next time.